So now we're into the second part of our presentation today. We're talking about new methods of construction. Up to now we've talked about rehabilitation of existing pipes and how to rehabilitate them and get them back up and give them a new lifespan. Now we're going to talk about new methods of construction. The first one we're going to talk about is horizontal directional drilling. Then we're going to talk about pipe jacking, pipe ramming, a bit of tunneling, and some pipe bursting. Pipe bursting is kind of a process that straddles both camps, but I'm putting it into new construction. Then I'm going to finish off a little bit on my favorite topic, which is carbon and the carbon reductions that we achieve through the use of trenchless technology, something that has been approved by the province of British Columbia to allow the cities of British Columbia a carbon credit, an internal carbon credit within their own operations by the use of trenchless technology. Horizontal directional drilling. It's something that a lot of people associate with trenchless in general. They kind of think everything is horizontal directional drilling. It's just one of the many ways of achieving trenchless technologies and the use of horizontal directional drilling. It can be used to install sewers down to half or 0.3% grade if the ground is suitable. The ground has to be fairly homogeneous. In other words, you can't work in till with cobbles in place, but it's very suitable with peats and clays and sands and silts and products like that. You can go from diameters with directional drilling from anything from 25 millimeters all the way up to 2 meters in diameter. And you can go from 2 meters in length all the way to crossing of the Congo River, crossing the Fraser River, crossing the Mississippi River. Horizontal directional drilling. It is a process whereby a drill rod is drilled into the ground and it is steered. And if you think of the end of the drill rod as being my hand has a little steering shoe on the front end here. Now I'm drilling into, at this point, I'm drilling into sand, silts, clays, softish materials. And I have a bent shoe at the end of my rod, at the end of the rod. And then I have a sub here, and in that sub I have a transmitter which transmits up the rotation, the inclination, and the depth. And a couple of other parameters to do with temperature and stuff like that. And then there's a little bit of a bend in this rod right here. So when this turns, it turns a bit of a sweep. And what that does, it creates a void in there that is bigger than the size of the shoe, and it allows material to run back. And you'll see it in the next shot here. And so that's directional drilling. Now, if you're going through in rock, you replace that shoe with a trichome bit, and that rotates as well. And both of those rotate in that manner. In other words, they sweep a circle bigger than their own diameter. And that creates a void here around the rod coming back up. That means when we're drilling, we're pumping mud down through the middle of the rod, out through this here, and either through a hole here if it's the plate, or if it's the trichome bit, it comes out through the bit pieces, and it mixes with the cuttings. And those cuttings and mud then go back up to the machine in that annulus that we've just done. I am putting this slide in here again because we're showing the limitations, or one of the limitations of directional drilling. When we directional drill, we generally directional drill from the surface down. So what is usable of a directional drill path is the section that's flat in the middle. Between the two, that flat section in the middle, between the 2 points E and D. So the section from G down to E and from D all the way up to A becomes unusable afterwards. It just becomes redundant. Where this becomes relevant is that if I am drilling between a tight area and a tight area, I need setbacks on both sides, and if I don't have that, I really can't use directional drilling as a process. The other thing we need to know about directional drilling is that if you're drilling a 25 millimeter or 50 millimeter or 100 millimeter diameter pipe, yeah, you can go across a road with that. You do not use directional drilling to drill across a 24-inch or 600 millimeter pipe across a road. You use pipe ramming and pipe jacking. If you're putting in a 24-inch or a 600 millimeter pipe, you should be going across the Fraser River or going, a length of 2, 3, 4 kilometers. Not a short length. Here we're now demonstrating a video on directional drilling. You will see you will see what they're talking about here. So we've got this demonstration of directional drilling. They're setting up, and here we're drilling under a canal and under a road. So they've got the drill rod set up. They're starting to drill. They're drilling into a pit. That pit is to recover that mud that I said that when I'm drilling, that mud that came back, that annulus, it comes back into this pit here. They capture that mud, they put it through sieves and screeners, and they take out the cuttings out and they reuse the mud back into the ground again. So you can see him drilling through here right now. He's drilling, I'm assuming it's he, probably being sexist, but that's, most drillers are males still. But he's drilling down, and you see the signals going to the surface. It is telling him the depth. It is also telling them the rotation, and it's also telling them the inclination of the pipe. And they can read that as a walkover. They can also read it back at the machine. They're coming now. They're going to hit a green pipe. So now they're going to stop. They're going to put the pipe at stop the drill rod at 6 o'clock, and then they're going to push straight. That's going to cause the drill rod to dive. And then they can start re-drilling it again. So that's how they control the drill rod, and they can get accuracies of about 50 millimeters or better. If you go back to a paper written in the late 90s by Richard Harper, he demonstrates about 5 kilometers of directional drilling that was completed in Queensborough and had accuracies of about 50 millimeters or better for a whole sewer system that we installed there in the 1990s. Here we're into the exit pit. Now we're attaching on a reamer, so we're going to open the hole up, and we're starting to pull back in the product pipe. Lots of times you would pull the reamer through 3 or 4 times to gradually open the hole up. It's unusual to go in with the reamer once and pull the pipe in once. You normally have to open the hole up and develop the hole before you can pull the pipe in. The hole that you're opening up is generally about 1.5 times the diameter of the pipe. In gravity sewers, you might go 1.2, 1.3 times the diameter, because you don't want the pipe floating around too much in that cavity. But in a regular force main or water main or an oil pipeline, you'll go 1.5. Again, if you keep the diameter low, your length is going to be limited. Pipe ramming. Pipe ramming is a very loud process. You can install anywhere from 300 millimeters to 3,000 millimeters diameter pipes. Grade is not as good as it is with pipe jacking, in that if you hit materials like there's cobbles or stumps, it can tend to push the pipe away and off grade and offline. But it does have the ability to go further, and it does have the ability to split rocks if they are on the way. Pipe jacking, you will come to a sudden stop if you hit a log, and you will come to a sudden stop if you hit a big enough rock with pipe jacking. But you can get the big diameters. You do need a reaction wall in pipe jacking, but you can have much better grade control if that's an issue, because you can use a pilot bore tubing to augment your accuracy. Tunnel boring systems. Tunnel boring is, well, it's a boring system. It bores through the ground. You can use tunnel boring, can be 3 meters. Generally, you wouldn't go less than 3 meters with a TBM or tunnel boring machine. So 3 meters and up. You can get up to channel tunnels or tunnels under the Alps, or tunnels in Norway, Sweden, and Europe, and the RAV line here is a tunnel boring machine. The RAV line and the line coming out of Coquitlam, they were both tunnel bored machines. So they're 7-8 meters in diameter. It's a person entry. In other words, there's a person inside controlling the system. It's, again, of course, this new construction. The pipe advances. This is one of the crucial things about tunnel boring machines. As the machine advances, the pipe advances with it. So the pipe comes up in segments inside the existing pipe, and then it's put into place as the machine moves forward. So there is no movement of the pipe in a TBM or a tunnel boring machine. The pipe, once it's put in place, it stays where it is and does not move forward. Microtunneling, in difference to that, is generally used for 400 millimeters up to, say, 2 meters in diameter, 2.5 meters in diameter. You are limited again to 150 meters, and that's because of the friction buildup, just like in pipe ramming, pipe jacking, pipe bursting. You're limited to about 150 meters in length. It's a non-person entry system. course, it's new construction. And the pipe is used to push the tunnel boring machine ahead. So the tunnel boring machine is chewing up the ground in front, and the compressive force against the face that it's cutting against is provided by the pipe pushing the tunnel boring machine from the back.